Hi everyone, we're talking about polynomial functions. In the previous video we had done the first two objectives, so in this video we're going to be picking up right here where we're going to identify the real zeros of a polynomial function and their multiplicity, and then we're going to go through quite a few examples. Okay, so let's start with identifying the real zeros of a polynomial. And so the zeros, that's another way to say where f of x equals 0. So that's the same thing as y. So it's basically saying when does your function equal 0, or when does it touch the x-axis. So these are all the same thing. X-intercepts, the zeros, when is the function equal to y, equals 0, and that's all finding the real zeros. Okay, so here is just a random example of a function in blue. And so all of these points are the real zeros when the function value, the y value, is 0. Okay, so notice sometimes you actually cross through, your function crosses through the point, like here and here. Other times your function might just touch that point, just touch it and come back down, and then cross through as well. So when we say crosses through, we mean cross through the x-axis. Otherwise, we mean touch, like it just touches and comes back down, or some people call this a bounce point, because it bounces off the axis and comes back. Alright, so our definition of a real zero. The real zero is the number, we're calling it r here, that when you plug it into your function, the result is 0. So when you take a number, you plug it into your function, and whatever number that happens to be, if the answer, when you do your computation, if the answer is 0, then that's what we're calling a real zero, the number that we plugged in. And so here is equivalent statements. R is a real zero of a polynomial function. That is also to say that it is an x-intercept on the graph. And an equivalent statement to that would be x minus that number is a factor when you write your polynomial. And then one more way to say the same thing is that it is a solution, a real solution to the equation when you set your function equal to 0. So all four of these statements are, all four are the same thing as far as what they're saying. So real zeros let us know we have an x-intercept on our graph, we have a factor in our polynomial, and that the number that we plug into our function, when we do that, we get 0 as the output. Okay, so let's take a look at this example now. Find a polynomial, part A, function with degree 3, whose real zeros are -1, 2, and 3. And then part B, we're going to graph. So we have degree 3, and we are going to use some of our facts that we just learned a moment ago about real zeros. And so we had 3 zeros given. We were told that -1 is a 0, that 2 was a 0, and that 3 was a 0. That means when I plug them into my function, each one individually, I'm going to get 0 as the output. But what that also means is that when we rewrite our function, f of x, that x minus the number that's a 0 is one of the factors. Okay, so that looks like this: x minus -1, x minus 2, and x minus 3 are all factors of our polynomial. So this is our polynomial. And so these are factors. Notice we have invisible multiplication in between here. And so these are all x minus r, x minus r, x minus r for our 3 zeros that were given. And it's degree 3, so there's no other factors, because if you were to multiply this out, you would have an x times an x times an x, giving us degree 3. Okay, so A, we put a number in the front here because A can be any non-zero real number. So we just found in general a polynomial with these zeros, because A can be any number, and it would, depending on what A is, it might stretch or compress our graph, or even reflect it if it's negative. And so if we just make a choice for A, we're going to say A is 1, and then go ahead and graph this. We can go to a graphing website or use a graphing calculator, and we would get this one, this polynomial functions graph. Notice where we touch and cross the x-axis at -1, 2, and 3. So those are our 3 zeros on our graph that we were given, and this will be the graph of the function. And then from last time, let me just sort of remind you of something that we just talked about in the last video. When you look at the power function here, because this was degree 3, if you multiply this out, you will get x cubed as the first term. That in behavior, that was an odd degree for your power function. And so the in behavior that we talked about last time was that the graph was going to go down to the left and up to the right. And that's exactly what happens here. Notice this goes down as we go to the left toward negative infinity, and this goes up as we go toward the right toward infinity. Okay, so now let's talk about something called multiplicity. So if we have a real zero, that when we plug it into our function, the answer is 0, then we have what's called the multiplicity of that 0, and that's how many times that factor occurs. So some books use the term multiple root or root of multiplicity, and pretty much this is the easiest way to notice it. It's going to look like an exponent, or if the factors are, for example, let's say they're written out, so like 2 would be the multiplicity here, or if we see them written out like this, how many times you see this factor occur. We see it happen twice, so this one would have multiplicity 2. Okay, that's how many times that factor occurs, and then in other words, that's how many times the real 0 occurs, or how many times you can plug in the real 0, and it would give you an output of 0. So technically for my example there, I can plug in 3 on 2 separate occasions and get 0 as an answer, because I can plug it in here and I can plug it in here. Okay, so let's do this example. For the polynomial here, 6x cubed times x minus 5 times x plus 1/4 to the 4th power. Let's look at the real zeros and their multiplicity. So this one has 0, the number 0 as a real 0 from this factor right here. If you plug in 0, this whole factor would be 0, right? Because if you think about it, 6 times 0 cubed equals 0. And the multiplicity on that one is 3. And you can tell from the exponent. Or if you want to work it out, if you want to write it out, expand it, it would look like 6 times x times x times x. So that's why that's multiplicity 3. I can technically plug in 0 3 separate times into my function here, and the answer would be 0. The second real 0 comes from here. This real 0 would be 5, because if I plug in 5 here, this whole factor would equal 0. Back here, if I plug in 0, we get 0. And this one only occurs once, because you either just notice you see the factor once, or you can look at this invisible exponent of 1. So that one has multiplicity 1. And then the last real 0 is from here. It's negative 1/4, because if you plug in negative 1/4 into this factor, you're going to get 0. And this one has multiplicity 4, you can tell from the exponent up here. Or if you want to think of writing that factor out 4 times, that's also how you can tell that the multiplicity is 4. Okay, so we had 3 real zeros. The number 0 was one of them, 5 was another one, and negative 1/4 was the last one. And they each actually had different multiplicities, for how many times we could plug the number into our function and get 0 as the answer. Okay, let's go ahead and do another example. This time we're going to be graphing. And real quick, just so you know, and I want to make this clear now, because if you maybe use a different book or you read this somewhere else, a real 0 is also called a root. So some books call it a root. So just so you are aware, they're called both. It's these numbers that when you plug them into your function, you get 0 is the answer. So this is the real 0 or the root. Okay, so for this polynomial function, f of x equals x minus 3 squared times x plus 4, we're going to do quite a few things. We're going to find the intercepts, and we're going to find the intervals when the graph is above, so when f of x is above the x-axis and below the x-axis, meaning that when our function is positive and negative. And then we're going to locate points on the graph, connect them with a smooth and continuous curve, so graphing the function. Alright, so remember, your y-intercept is always found by letting x equal 0. So just plug 0 right into your function, right where there's an x, and if you simplify, you're going to get 36. And so that y-intercept is going to be the point 0, 36. And then remember x-intercepts, that's when you let y equal 0. So you set your whole function equal to 0, and then you solve. And so since this is factored, we can do this one pretty quickly. If you know your zero product property, let me just remind you how that works. Your zero product property says if you are multiplying two or more factors and the product is 0, then one of those factors had to be 0. Okay, and hopefully that makes sense. If you multiply two things and then the answer is 0, well, one of them was 0 to begin with. And so that's what you use here, because we are multiplying these factors. So either x minus 3 squared is 0 or x plus 4 is 0. And then if you solve both these, even though this one is squared, you can just think of it as taking the square root on both sides. And you're going to get 3 and negative 4. And so those are actually our x-intercepts, but are real zeros as well. So remember, x-intercepts are the same thing as your real zeros, or your roots. So you have negative 4 and 3. Okay, so we have two x-intercepts, and it's going to end up cutting our x-axis into 3 parts. So let's just put that here really quick so you see what I'm saying. When we go to graph, we're going to have our x-axis. I'm going to just put 0 for reference, and then negative 4 was one of our x-intercepts, and 3 was another one. Okay, and so notice what it does to your x-axis. When you go to graph your function, it actually splits your x-axis into 3 parts. So let's make sure you can see this here. It would have one portion over here to the left, we'll call this part portion 1, one portion here in the middle, call that portion 2, and then another third portion onto the right. And so what you want to do is you want to see what happens on the left and the right of those x-intercepts. Okay, so we know at the x-intercept that our graph is either going to actually touch or just touch or cross through those points. So we need to know what happens around it. Are we below or are we above the x-axis? Okay, and so what we're going to do, and one way to work this out, is to actually just pick numbers in these 3 areas, these 3 intervals, and then see where you're going to have points. Okay, so we have from negative infinity to negative 4, we're going to pick a number. Anywhere between negative 4 and 3, we're going to pick a number, and then anywhere from 3 to infinity, we're going to pick a number. And so here we're using a table to kind of keep it all organized. So this is a choice. So number chosen, pick anything you want. So pick anything you want, and this is on the left of negative 4. So you can pick negative 5 like we are, or negative 6, or negative 1,000,000, whatever you want to pick. So you can pick anything you want over here. And then in the middle neighborhood, pick anything you want here, and you could pick negative 3, negative 2, negative 1, and so on. And we're going to pick negative 2, okay? And then on the right of 3, pick, again, anything you want. We're going to pick 5. And what you do is you're going to plug those into your function. So if you go back to your function and you just plug those numbers in for x, Negative 5 is going to give you a y value of negative 64. So that's the point on the graph, x comma y. If you plug in negative 2 into your function, you're going to get out 50. And then that point's on your graph. And then if you plug in 5 into your function, 5 comma 36 is on your graph as well. And so the location in the graph is just set, if it's negative, if your y value is negative, you are below the x-axis. And if your y value is positive, then you're above the x-axis. Okay, so now that we've done some side work with our table here, we have quite a bit of information to go ahead and graph our function. And so starting with our intercepts, we had negative 4, comma 0, 3, comma 0 for our x-intercepts, also called the real zeros. And then we had a y-intercept, 36. Okay, so those are the points we found by computing. And then the next few points we found by using our table and just choosing numbers. So we plugged in negative 5. That point is way down here. We can't quite see it, but it's way down there. Negative 2 we plugged in and got out 50. So that's that point. And then 5 we got out 36. And then we connect our points. So what you do after that is if you have enough points, then you just take your smooth curve and you say, okay, there was a point way down here and I have to touch this x-intercept, and then my next point is up here, so I'm going to have to go through there. I'm actually going to cross, and then my next point is down here, right here on the y-axis, so I know I need to come back down and hit that, and then my next point is right here on the x-axis, and then I have one more point that I found, and it's going to go up right there, okay? And it's going to keep going up. And so that is our graph. And so a quick reminder also from the previous video, the end behavior of this function. If you think about multiplying out our function just from right here at the bottom, we have x squared times x. So if I just kind of put all those together, without actually foiling the whole thing out, I know that that's going to give me x to the third, and some more terms, but what I want to focus on is that it's x to the third. So x squared times another x is x to the third, and so it's odd. We talked about this before, but odd degree. So the end behavior is going to go down to the left and up toward the right, which is exactly what happens on our graph here. Okay, so the next thing we need to mention is something called a turning point. And a turning point, if you are graphing a function, it's where it looks like it's turning. And so it would be where we go from increasing to decreasing. That would be a turning point right there. Or from decreasing to increasing. That would be a turning point right there. So if you were to travel along this graph, let's say you were driving your car along this graph. Here's my nice picture of a car. Okay, this is where you would turn. Those are the turning points. And what we know about them for polynomial functions is that if your degree of your function is some number n, then your graph turns at most one less than that. So for example, if your degree of your function, let's say, is 4, then your graph turns, so turning points is 3 or less, one less than that. So if your degree is 10, then your turning points is 9 or less. It's going to be your degree minus 1 at most. So let's try this example. So which graphs on the next slide could actually be polynomial functions? And then if they are, we're going to find the real zeros, and then we're going to state the least degree that the polynomial can have. So the least degree that it can have. And then if it's not a function, polynomial function, we'll say why not. Okay, so take a look at this one. This is a smooth curve, but there's a jump. It's not continuous. So this is not a polynomial function because we cannot have this gap, no gaps. It has to be a smooth, continuous curve, which we talked about before, but let's just put that here. Smooth, yes. Continuous, no. Uh-oh, so that one was not a polynomial function. How about this one? Smooth curve, continuous curve. Yes, this one is a polynomial function. So now that we know it is, we have to find the zeros, and they're here. So this is at -3, -1, and 1. Okay, so we got 3 zeros. And now the other question was about the degree. And so this graph, look at the turning points. If you were traveling on this graph, it would have one turning point here, and then down here would be another turning point. So there's 2 turning points on your graph, and based on the theorem we just learned, that means that the degree of our polynomial is 3 or more, okay? Because if the degree is 3, then we had 2 or less turning points. So we kind of just worked it backwards. We said if we had 2 turning points, then the degree has to be at least 3. So this is a degree 3 at least polynomial. All right, how about this one? Is this a smooth, continuous graph? No, it is not, because this corner is not considered smooth. This is really sharp. So this is a sharp corner. So this is not the graph of a polynomial function. We call this one not smooth. It's continuous, but it's not smooth. This one here, this is a smooth and continuous function. So this one is a polynomial function. And let's identify the zeros. There's one right here at -3, and another one here at 0. Okay? And then what is the degree of this polynomial? So we're going to use the turning points. This graph has 3 turning points. Right here, we're going from down to up, decreasing to increasing. Right here, going up to down, increasing to decreasing, and one more, down to up, increasing to decreasing to increasing. So we have 3 turning points, so then our degree is at least 4. So the degree 4 has 3 or less turning points. And so we just worked it backwards. We started with the fact that we had 3 turning points, so we knew that the degree had to be at least 4. All right. Now the last things we want to talk about in a few more examples is the end behavior. So we briefly touched on this on the last video, and it was on our power function. Okay, so the end behavior of this polynomial function. So this is our polynomial function that we defined last time. Okay, and this is just in general, where n is the degree. The behavior of this graph on the ends of the graph, behaves the same as the power function graph. And so if you notice, this is just your leading term. So yes, we'll have all these other terms in the back, but if we focus on just this leading term, which is our power function, x to some power here, then whatever this behaves as on the ends, then so will our whole function, our whole polynomial function. And here are your 4 possibilities. So 4 possibilities, and it just depends on what's going on with your particular function. So we have with even degrees. So if the degree of your polynomial, let me kind of split this in half here. If the degree of your polynomial is even, okay, so you have 2 or 4 or 6 or 8 or something right here for the highest power on x, then your graph is either going to go up left and up right as x goes to negative and positive infinity, or it's going to go down left and down right. Okay, so when we first just learned about our power function, we only focused on the one that goes up. However, if your leading coefficient is negative, then your graph's going to flip. It's going to flip and go down. Okay, so let's talk about the odd, and then we'll kind of sum this up. If your degree on your polynomial is odd, so 3, 5, 7, 9, etc., then your graph goes either down left and up right on the ends, or the opposite, up left and down right. And it flips if your leading coefficient again is negative. So 4 possibilities. First, you have to decide, is your degree of your function even or odd? Okay, so if it's even or odd, if it's even, it's either going to go up, left, up, right, or down left and down right. If it's odd, they're going to do the opposites of each other. They're going to go down, left, and up, right, or up, left, and down, right. And then the difference is the leading coefficient. So if the number in the front is positive leading coefficient, this is going to go up, and this one's going to go up, left, down, left, and up, right. If your leading coefficient is negative, then your graph flips. So it's going to go down, left, down, right for even, and up, left, down, right for odd. Okay, so hopefully that sort of is kind of making sense to you. It'll make more sense the more examples you go through, but you have to figure out your 4 possibilities, starting with, is your degree even or odd? Then, is your leading coefficient positive or negative? So leading coefficient, just going to abbreviate, positive or negative. And so those are just the 2 questions you have to ask yourself. Once you've asked those 2 questions, you'll be able to figure out which of these 4 situations your graph has as far as the end behavior. Okay, so let's try to put this together. Which graph in the figures could possibly be the graph of this function? So we have 4 choices, and we're going to pretty much use process of elimination here. So our function is f of x equals x to the 5th plus a x cubed plus bx squared minus 2x plus 3. So what we want to notice is this leading term, and think of our power function. So this is 5th degree, so degree 5. So degree is 5, which is odd. And then the leading coefficient on this one is an invisible 1, which is positive. So positive. Okay, so we need both of those pieces of information to be able to figure out this graph. And so right away, and we'll sum this up on the next few slides, but right away we can eliminate some of these graphs. Let's think about it. Okay, so since it's degree 5 and it's odd, the ends of the graph are going to either going to go down, left, and up, right, or up, left, and down, right. And then because it's a leading coefficient that's positive, invisible 1 right here, it's going to be this case. So this was a positive leading coefficient. This one over here was a negative leading coefficient. So that means I can get rid of choice D. It's not graph D. Okay, so we used both of these pieces of information so far. What else can we use that we've learned so far? We can use what we learned about turning points. So because the degree is 5, that means that the graph has how many turning points? Well, degree 5, it has turning points 4 or less. 4 or less. Okay, so let's see. This graph has way too many turning points. It has 1, 2, 3, 4, 5, 6, 7, 8. So it cannot be graph C. Way too many turning points. So let's count on graph B. 1, 2, 3, 4. That one's okay. Graph A, 1, 2, 3, 4 as well. So it could be A or B, and so now we have to figure out what else can we use to figure out the graph of this function. And if you take a look, what we know, even though we don't know exactly what these numbers are for a and b, we do know the y-intercept. If we plug in 0 for x, okay, look what you would get. This term, the first term, second term, third term, and fourth term would all go to 0, and we would get 3. Out of your 2 choices remaining, only this one has a positive y-intercept. So that gets rid of choice A, and it has to be B. Okay, so we just, we kind of did all that and just sum it up here. So our y-intercept let us eliminate one of our choices. Okay, and then we looked at our end behavior and saw how that was affected by a 5th degree polynomial, odd degree. And then even though we weren't able to solve for our x-intercepts because we didn't actually know the whole function, it had a and b in it, we still could use the turning points to eliminate other choices. And so then our only choice was graph B. Okay, one last example. We're going to find a polynomial function whose graph is this one here, and we're going to use the smallest degree possible. So we want to identify some important things on this graph, the zeros. Okay, so we have -1, 1, and 2. We also have a y-intercept, and we know the end behavior. It goes up, left, and up, right. And then let's count the turning points. 1, 2, 3 turning points. Okay, so we're going to use all of that to figure out a possible function for this graph. Okay, so let's put all of that together. So our x-intercepts are our real zeros, and remember those tell us our factors. So that means that x minus each of our real zeros is going to be a factor. So we have x minus -1, and then x minus +1, and x minus 2. So we know those 3 factors go into our function. Then we counted 3 turning points, so that means the degree of our polynomial has to be at least 4. So remember, degree 4 would mean 3 or less turning points. So just working backwards, we know that 3 turning points means at least degree 4. Now this part has to do with the multiplicity, and I want to show this example because it's actually important to know what happens if the multiplicity is even or odd, and we would know that from how the graph looks. Okay, so if your graph touches the x-axis, that actually means that we have an even multiplicity. So right here where we just touch the x-axis and come back up, that's going to be even. And if you think about it, that's because the graph behaves, if you sort of zoom in right here, it behaves like a parabola, like x squared would behave. And so that would have an even multiplicity. And then if it crosses through the x-axis, like it does here and here, those ones would have odd multiplicity. And that's because if you think about maybe the x cubed function, it crosses through the x-axis. So this is an important thing to note, and just kind of keep this on hand. If your graph touches the x-axis, your multiplicity is even, and if your graph crosses the x-axis, your multiplicity is actually odd. So that's going to help us also in finding this function. Alright, we're almost there. So we're going to use the smallest degree possible. So for odd, we're going to pick 1, and for even, we're going to pick 2. And so for our zeros and their multiplicities, we know for a 0 of -1, this one here, the multiplicity was even, so we'll give it a 2. And for the other 2 zeros, the multiplicity was odd, so for each of those, we're going to give them an invisible 1. And then this is our polynomial function, but we're going to add in this leading coefficient here of a, because we could have some number there, we just don't know what it is yet. And so now we have to do our last step, which is to find what a equals using the other point we haven't used yet, which was our y-intercept from our graph. And so from our y-intercept, we know that y is 4 when x is 0. So we're going to plug in 0 into our function, set it equal to 4, and that's going to allow us to solve for a. And so a is 2. And so our final answer, our polynomial function, is f of x equals 2 times x plus 1 quantity squared times x minus 1 times x minus 2. And so we got that whole function from just seeing a graph and knowing the zeros on the graph, identifying that this was going to be an even polynomial, and then we learned about the multiplicity, how this was even multiplicity at this touch point, odd multiplicity at these cross points, and then we used the fact that this graph had 1, 2, 3 turning points. Alright, so we did it. We learned a lot about polynomial functions and graphing them, so thank you for watching.